Hello and welcome everyone, and thank you very much for joining today's LVA webinar on setting the foundation for analytical excellence, the next generation of reference materials. My name is David Steiner and I am the head of the reference material division here at LVA, Austria's largest private food testing laboratory. I hold a doctoral degree in food and biotechnology from Boku University, and I am now already working for more than 10 years in the field of mycotoxin analysis. In addition to my current role at LVA, I have also held various leadership positions, including Valneva and Roma Labs, which has given me a broad perspective across both analytical laboratories, but also industrial environments. And I'm also very happy and proud to being actively involved in international expert groups such as the AOAC, where I contribute to the development of analytical methods for mycotoxins, particularly in the context of novel foods. So with that brief introduction, let's now move into the topic of today's webinar itself. And to set the stage, I would like to start with the fundamentals of reference materials. So before we go into too much details and advanced aspects and also recent developments, I think it's very important to understand what reference materials actually are and why they play such a critical and crucial role in analytical chemistry. So what exactly do we mean when we talk about reference materials? In very simple terms, a reference material is a material with well-characterized properties that can be used in analytical measurements. But their value goes far beyond just being a defined material. They are actually essential for ensuring the accuracy of our analytical results and also for validating that our methods are actually performing as expected. So in addition, they also allow us to compare results between different laboratories, which is especially important in regulated areas such as the food safety area. Reference materials also play a key role in quality assurance, helping us to continuously monitor the performance and also to detect potential issues early on. And the last point is particularly important. They often serve as an early warning system for systematic errors in the analytical process. So overall, we can say that reference materials are not just supporting tools, but really a central element in generating reliable and especially defensible data. And depending on the specific application, different types of reference materials are used. So let me briefly walk you through the most important categories. So first we have so-called neat standards, solid standards which are highly concentrated pure compounds. These are typically used for spiking experiments during the method development phase or for preparing calibration levels in-house. However, their reliability strongly depends on an accurate purity assessment. Then we have calibration solutions. These are usually gravimetrically prepared and come with assigned concentrations and also a defined uncertainty. And because of their traceability, they are essential for an accurate and comparable quantification. A particular important category are so-called matrix-based reference materials. These materials are either real or so-called simulated samples. That means they can either originate from naturally contaminated raw materials such as maize or wheat, allowing us to evaluate the analytical performance under very realistic conditions, including, for example, matrix effects, but also the extraction efficiency. On the other hand, they can also be fortified or spiked materials, especially in cases where naturally contaminated material is not available or limited. So next we have internal standards. Internal standards are compounds that are added to the sample in a known amount and they behave very similarly to the target analyte during the entire analytical process. A particularly powerful approach is the use of so-called isotopically labeled standards like C13 labeled compounds. These have the same chemical structure as the target analyte, but a slightly different molecular mass due to the isotope labeling. And this allows us to clearly distinguish them in the mass spectrometry, while they still behave almost identically during the extraction, also the cleanup and the ionization process. And as a result, internal standards can be used to correct for losses during the sample preparation and especially for unwanted matrix effects during the ionization process in the mass spectrometer. And finally, we have cultural materials. These are not classical reference materials in the strict sense, but they are widely used in experimental settings such as feeding trials or metabolism studies. And because of their application, they still require a quite high level of control and quality during the production. That's why they are similar to classical reference materials. So overall, each of these material types addresses a different part of the analytical challenge. And only by combining them, we can really ensure a robust and reliable workflow. And typically this process of this workflow starts with the sample preparation. At this stage, internal standards can be added prior to extraction to correct for extraction losses and matrix effects. However, this approach is relatively costly, which is why in routine analysis, internal standards are often added at a later stage, typically during the quantification step. In addition, matrix-based reference materials are often processed alongside routine samples during the sample preparation step. This allows us to simulate the entire analytical workflow from the sample prep to the final measurement. Neat standards in this case are mainly used here for spiking experiments, as I already mentioned before, especially during the method development or during the validation phase. When we move on to the quantification step or to the analysis step, hereby calibration solutions are used to establish the calibration curve, which is essential for quantification, while internal standards here help to correct simply for matrix effects. In this context, a so-called CEDA approach is commonly applied. CEDA stands in this case for stable isotope dilution assay, where a defined amount of an isotope labeled internal standard is added to each sample and also each calibration level, typically via the autosampler. And this helps to reduce the amount of the internal standards which is applied at the end, because a very small amount is sufficient in this case. So after the analysis, we already entered the quality control and data evaluation stage. Hereby, matrix-based reference materials play a very important role as they allow us to verify whether the method was performing as expected or not. And that's why in many cases, the materials are also called QCM materials, which stands for quality control material. In some cases, proficiency testing materials can also be used for external benchmarking. So after the QC evaluation, we have either the decision that the data are acceptable, or in a negative way, the data have to be rejected. In this case, we enter the last phase, the corrective action phase. So in case of a deviation, we have to figure out what was the root cause of the problem. And this could involve a reanalysis of the sample by using another matrix material, or also to recalibrate by using different calibration standards. And now at this point, it is also very important to highlight that not all reference materials are the same. Even though they may look similar in practice, they are significantly different in terms of quality, traceability, and also reliability. So on the one hand, we have classical reference materials, which are generally suitable for routine analytical use, such as method development or internal quality control. They are typically homogeneous and stable, but the assigned value may not be fully traceable and are often provided without a defined measurement uncertainty. On the other hand, we have so-called certified reference materials, or CRMs. These are characterized using validated metrologically sound procedures. Their assigned values are always accompanied by a defined measurement uncertainty, and they are traceable to SI units or internationally accepted references. This makes them particularly important whenever results need to be comparable, defensible, or used in a regulatory context. So the key message at this point is a CRM is not just a reference material, it is a reference material with proven accuracy, traceability, and a quantified uncertainty. And in practice, this means that while reference materials can support your workflow, a certified reference material is essential when your result must truly be reliable and comparable. Now coming to one of my favorite slides, to better understand where we are today, it is always very helpful to briefly look back at the origins of reference materials. And one of the earliest and most well-known examples as for a reference material is the so-called Bowen's scale. This was developed in the 1960s by this gentleman in the small picture here, Humphrey Bowen. He was a British chemist. At that time, the goal was to create a homogeneous and stable material that could be shared between different laboratories to improve the comparability of their analytical results. And in this case, a very large batch of around 100 kilograms of dried and ground kale was produced and distributed to laboratories all over the world for many, many years. So while this material would not meet today's requirements for certified reference material, it established a very important concept, the idea that laboratories need a common reference point to ensure comparable and reliable measurements. And this concept essentially laid the foundation for the development of modern reference materials. And building on this idea, the field continued to evolve, especially with increasing importance of mycotoxin analysis. So in early stages, as we could see during the 1960s and 70s, reference materials in general were already being developed, mainly as biological matrices, like the Bowen scale, as we could see. However, for mycotoxins, there were still no well-established or widely available reference materials at that time. As analytical methods for mycotoxins especially started to evolve, laboratories often relied on in-house approaches using neat standards for spiking experiments to support the measurement. And it was not until the 1980s and 90s that the first real dedicated mycotoxin reference material was developed. These included both neat standards and also early matrix-based materials such as contaminated grains or milk powder. So during this period, the first certified materials emerged, for example, for aflatoxin M1 in milk, largely driven by increasing regulatory requirements. And in the following years, standardization became more and more important, with organizations such as the European BCR program contributing to the development of certified reference materials and introducing key concepts like uncertainty estimation and also traceability. And in more recent years, we have seen a very strong shift towards multi-mycotoxin approaches, advanced analytical techniques such as LC-MS, and also the implementation of ISO standards, particularly ISO 17034. And in the next section, I would like to briefly introduce this ISO framework with a particular focus on the ISO 17034, which defines the requirements for reference material producers. This will help us to better understand how quality in reference materials is defined and actually ensured today. So let's take a closer look at what ISO accreditation actually means. So ISO standards are internationally recognized frameworks that define requirements to ensure quality, consistency, and comparability across laboratories and organizations worldwide. In the context of analytical laboratories, different standards apply depending on the scope. For example, the ISO 17025 defines the requirements for testing laboratories. ISO 17034 on the other side for reference material producers. Accreditation according to these standards serves as an official confirmation that the laboratory or organization operates in a technically competent and reliable way. And on this slide, you can see an example of such an accreditation certificate issued by the Austrian accreditation body. This is the official recognition that LVA meets the requirements of the ISO, of a respective ISO standard, in this case for ISO 17034. In other words, LVA is an accredited organization and an accredited reference material producer. So in practice, ISO accreditation is not just a formal requirement, it is a clear proof of quality and competence, and it ensures that results generated under these standards are reliable and internationally comparable. So for reference materials, it means ISO standards provide the framework that turns a reference material from a useful tool into traceable and reliable measurement anchors. So before the ISO standard was introduced, there was no fully harmonized international standard for the production of reference materials. Instead, producers relied on a guideline, the so-called ISO Guide 34, which already defined general requirements, but was not part of a formal accreditation framework. Between roughly 2009 and 2016, a transition phase took place where this guideline was gradually transformed into a fully harmonized ISO standard. And this resulted in the publication of the ISO 17034, which now defines the competence requirements for reference material producers. One major advantage of this transition was the alignment with other standards from the ISO 17000 series, especially the ISO 17025. This means that laboratories already accredited under ISO 17025 could integrate their existing quality management system and mainly focus on implementing the additional technical requirements specific to reference material production. At the same time, ISO 17034 is still a relatively young standard within the series, and this is also reflected in the ongoing development of its companion documents. So new standards and updates, for example, related to characterization stability or the production of QCMs, are continuously being introduced and refined, what you can see here in this graphical overview. But how does all this influence the assignment of a certified value of a reference material, the overall target, if you want? So one important point to highlight right at the beginning is that a certified value is never just a number. It is always accompanied with a defined uncertainty. And this uncertainty reflects the influence of different steps throughout the entire production until the final characterization. Starting with the production, the quality of the raw material plays a very crucial role, especially its purity. But there are also influencing factors coming from the testing equipment or environmental factors. Another important factor is homogeneity. A material needs to be sufficiently homogeneous to ensure that each unit represents the same value. This is typically easier to achieve for liquid standards than for matrix-based materials. The next aspect is stability, which is usually divided into short and long-term stability. The short-term stability study is designed to simulate transport conditions, often over a period of several weeks and always under elevated temperatures, such as room temperature or even higher. Long-term stability, on the other hand, addresses storage conditions, over an extended period of time, often several years. So finally, we have the characterization, which includes the analytical method used to verify the final value. Here, factors such as method selection, precision, and also the interlaboratory variability all play a very important role. So all these components contribute to the final certified value and especially to its associated uncertainty. And because each step within the ISO accreditation is carefully controlled and documented, the entire process is fully traceable, ensuring a high level of comparability and confidence in the result. So after looking at the factors influencing certified values, I would now like to focus on one particular critical aspect, namely the determination of the purity of a neat standard. In practice, this is an area where there is still some degree of flexibility in how reference material producers apply their analytical methods. However, from a metrological point of view, there is a clear preference for a so-called primary measurement method. And in this context, we're talking about a quantitative NMR or qNMR, which has become increasingly important in the last couple of years and decade. So a qNMR measurement allows direct quantification of the compound of interest without the need of an external calibration, and it also allows the application of internal standards. This makes qNMR a highly accurate and traceable method for the purity assessment. In contrast, many commonly used techniques such as HPLC-based methods are considered secondary measurement methods when used especially for the purity determination. So these methods always require calibration with the substance itself, meaning that the standard of known purity is needed in the first place, which essentially creates a circular dependency, or in other words, a chicken-egg problem. So for this reason, such methods are often more suitable for assigning values to working standards rather than for the direct determination of the purity itself. So after covering all this theoretical framework, I would now like to shift the focus to the practical experience. So during the development of our reference material portfolio, which already includes quite a broad portfolio of liquid reference standards, also isotopically labeled standards, and matrix-based reference materials, we have made a lot of different observations, and some of them has been quite unexpected. And let me now show you just a few examples of where theory and reality do not always fully align. So one of the first examples I would like to show is based on an HT2 toxin neat standard we received from one of our suppliers. As we discussed earlier, qNMR in this case would represent the state-of-the-art approach for the purity determination. However, in practice, many manufacturers still rely on secondary methods like HPLC or even thin layer chromatography, as also indicated in the certificate shown here. So this is mainly driven by cost considerations, as qNMR requires a significant amount of the neat standard material, and that can be relatively expensive, up to several thousands of euros, and some manufacturers just try to save some costs at this point. So according to the certificate, the purity of this material was reported to be around 98 to 99%. So for our accredited reference standards, however, we always perform qNMR analysis in collaboration with an ISO 17025 accredited partner lab specialized in the purity determination. And in this case, the actual purity was determined to be closer to 89%, which is a quite big discrepancy of around 10%, which is already quite significant when it comes to routine testing at the end. However, with the next example, I would like to show you that even quantitative NMR, although it is very powerful, can also have some certain limitations, especially when dealing with more complex analytical challenges. In this case, we are looking at a certificate of fumonisin B2, where again, a purity of close to 99% was reported based on HPLC and thin layer chromatography, so the same story. There is also a reference to NMR, but without any quantitative value. It simply says it complies. So for this reason, of course, we again sent the material to our external partner laboratory for the full qNMR analysis, and the result showed a purity of around 94%, which is lower than expected, but still acceptable for our starting purposes, although ideally we would aim for values above 95%. And based on this result, we decided to proceed and use the material for the production of the first test batches and started with the gravimetrically production of the liquid standard. So, however, after performing this manufacturing step of the first batch, we also performed our routine quality control measures as part of the final product release testing. And in this case, we have performed a triple quad analysis. And at this stage, we observed a quite significant deviation. So the purity was no longer close to 94%, but dropped to approximately 50%. In addition, we also detected a total of 11 impurities in this product, what you can see here in this HPLC-MS chromatogram. So at this point, for us, it was quite clear that we had to go back to the beginning and also investigate the root cause of this issue. So we are now in the corrective measures phase again. And to better understand the root cause, we compared the questionable lot of fumonisin B2 with a second lot where we already knew that the purity was very high, close to 99%. So we performed an additional NMR analysis using a different laboratory, and here you can see two spectra, the questionable lot on top and the high purity material below. And at first glance, both spectra actually look quite similar. However, with a closer look, subtle differences become visible. So the experienced NMR analyst can identify here some variations in the signal intensity and also slight differences in peak patterns, indicating that the composition is not identical. So what we are dealing here is a contamination with a so-called structural analog, a compound that has a very similar chemical structure to the target analyte, but it is not identical. In this case, this is particularly relevant because fumonisin B2 belongs to a family of closely related compounds, including fumonisin B1 and fumonisin B3. Fumonisin B2 and 3, for example, are structural isomers. They have the same molecular weight and a very similar structure, but they differ in the arrangement of their atoms. This makes them extremely difficult to distinguish analytically and also difficult to fully separate during the purification. So it is very likely that the impurity we observed originate from the fumonisin family itself, which explains why they were not easily detected in the initial analysis. To further investigate this issue, we also performed 2D NMR analysis, and as you can see here, the results clearly confirmed the presence of impurities in the questionable lot. So on the left side, you see the contaminated sample where complex impurity patterns appear below the target analyte. and in contrast, the spectrum on the right shows the high purity material with almost no interfering signals. And this actually highlights how challenging it can be to fully detect and separate structurally similar compounds. And at this point, I would like to emphasize two key aspects. First, purity assessment is absolutely critical when producing reference standards. But equally important is release testing as complementary quality control step. Each batch needs to be verified again, ideally using independent methods. And in the best case, this verification is performed using external reference materials, preferably certified reference materials, to ensure the highest level of confidence in the final product. However, it is also clear that these efforts are both time-consuming and costly. And for this reason, some manufacturers may just choose to simplify certain steps in order to save time and resources. And based on this assumption, and also based on our observations, we became curious about the overall quality of reference standards currently available on the market. So about 2 years ago, we conducted a multi-supplier study focusing on mycotoxin standards. In total, we analyzed 30 standards from 10 internationally recognized producers, covering key mycotoxins such as aflatoxin B1, deoxynivalenol, and zearalenone. And to ensure the comparability, all standards were adjusted to the same concentration level and analyzed in triplicate. The measurements were performed using LC-MS in collaboration with Boku University, as well as HPLC UV at LVA. So based on this, we have also established individual acceptance criteria, taking into account the uncertainty stated in the certificate, the analytical variability from the two methods, and also the influence of the uncertainty coming from the sample preparation. And the results of this multi-supplier study are summarized in this graphic. So on the y-axis, you can see the results obtained by LC-MS. On the x-axis, the results from the HPLC from LVA. From a correlation perspective, we can see that we have a very strong and good agreement between the two different methodologies. And ideally, all values should be close to the 100% center, since all the standards were adjusted to the same concentration level. However, as you can see, the results are widely spread. So some values are significantly below 100%, around 80, which may indicate stability issues or degradation effects of the standards. On the other hand, we also observed values up to 115%, which likely points to evaporation effects, for example, due to improper vial sealing. The positive aspect, however, is that all ISO 17034 accredited materials met the expected performance criteria, typically within a very narrow range of around plus minus 3% of uncertainty. And this clearly demonstrates the benefit of this standardization and the accreditation which already took place. However, overall, about 1/3 of all the suppliers were outside their individual acceptance ranges. Many of these deviations were in the range of 5 to 10% below the target value, which again reflects the purity issues we've just discussed earlier. In addition to the quantitative results, we have also performed high-resolution mass spectrometric analysis at the university in Szeged in Hungary in order to investigate the presence of impurities in the different standards. So in total, we detected 11 impurities in the deoxynivalenol standards, 9 in the aflatoxin B1, and 8 in the zearalenone standards, distributed across multiple suppliers. What was particularly concerning was the nature of some of these impurities itself. So for example, We found significant amounts of aflatoxin B2 and G1 in aflatoxin B1, and we have also observed notable levels of zearalenone in the deoxynivalenol standard with up to 3.5%, as well as traces of related compounds in the zearalenone standard itself. And these findings clearly indicate issues related to insufficient purification or cross-contamination during the production. And once again, this highlights the importance of a robust and complementary quality control system, which allows us to identify such issues and also to verify the true quality of the final material. So to summarize this part on liquid and especially neat standards, we have seen that there are several critical steps to consider in order to ensure very high quality materials. So first, purity assessment plays a very central and crucial role. Quantitative NMR clearly represents the state-of-the-art approach and provides a much more reliable basis compared to secondary methods. However, purity testing alone is not sufficient, as we could see. A complementary quality control system is really essential, especially to detect structural analogues or potential cross-contaminations. In this context, batch release testing becomes a very critical step to verify the quality of each individual production lot. Many of these aspects are already addressed within the ISO 17034 framework, which has significantly improved the overall quality of reference materials on the market. However, as we have seen, there are still some gaps, particularly when it comes to the consistent application of advanced techniques such as the qNMR. And finally, stability is another key factor. Deviations below expected concentration levels clearly indicated that stability is not always sufficiently controlled. So under ISO 17034, stability testing and long-term stability monitoring are mandatory, and this is essential to ensure that the assigned values remain valid over time. All right, so far we have mainly looked at liquid or neat reference standards. Now let's move one step further and take a look at matrix-based reference materials. So starting with our first matrix-based reference material, we decided to prepare or develop a maze-based matrix material, as it is one of the most relevant and widely used matrices in mycotoxin analysis. In many cases, manufacturers rely on spiked materials to cover a broad range of analytes. However, such materials do not always reflect real contamination patterns, and also the availability of naturally contaminated reference materials on the market is still quite limited. Therefore, we clearly decided to develop such a fully naturally contaminated maze matrix material. And for this purpose, we used 5 highly contaminated maze batches covering different mycotoxins such as aflatoxins, fumonisins, deoxynivalenol, or ochratoxin A. And these were combined with a larger number of blank or lower contaminated batches to achieve at the end the desired concentration levels. So in total, more than 30 individual batches were homogenized and pre-tested in-house using LC-MS to understand their individual contamination profiles. Homogenization was performed using an ultra-centrifugal mill to obtain a really fine powder and uniform powder, which is essential to ensure homogeneity. And the final material was then produced in several mixing rounds, combining contaminated and blank maze to reach at the end the target concentration levels and really ensure that the material is fit for purpose and homogeneous. And after the production, the final batch was again analyzed by LC-MS to assess the overall contamination pattern and to obtain a first indication of the homogeneity. We have also investigated the particle size distribution. In this case, the particle size distribution was analyzed using a so-called laser diffraction method within an ISO 17025 accredited laboratory. So in this case, one key parameter here is the so-called D90 value, meaning that 90% of all the particles are smaller than this size. And in our case, this value was around 300 micrometers, which corresponds roughly to a US mesh size of 50. So this indicates again that the material is a very fine powder and already suggests that a very good level of homogeneity was reached. The stability of the material is evaluated over a period of 36 months, so 3 years. So for each time point, 3 replicates are stored to allow for triplicate analysis at defined intervals. For example, after 1, 3, 6, or 12 months, the samples are transferred from the regular storage to minus 20 degrees. So this temperature is used as a reference condition where the material is considered stable and no further degradation is expected. The LC-MS analysis is then performed in an isochronous design, meaning that all time points are analyzed together after 12, 24, and 36 months. So this approach ensures a very reliable assessment of potential changes over time and is fully aligned with the procedures we also apply, for example, for our accredited reference standards. One of the most critical steps in the development of matrix-based reference materials is the characterization through an interlaboratory comparison study. In our case, we conducted such an interlab study involving 13 laboratories worldwide. Each laboratory received 3 replicates of 30 gram and was asked to analyze each replicate in triplicate, resulting in a total of 9 data points per analyte and laboratory. 2 laboratories, in this case, provided 2 independent data sets. So in total, we obtained 15 data sets for the characterization of this material. These included 10 LC-MS data sets, 3 high resolution, as well as 1 ELISA and 1 HPLC UV-based data set. 8 of these data sets were generated under ISO 17025 accreditation, and the majority of the laboratories applied a stable isotope dilution approach, meaning the use of internal standards. And this ensured a very high level of analytical quality and also comparability across different methods and laboratories. In addition, we have also evaluated the applicability of the material for lateral flow devices. This is particularly interesting as in practice, materials are often developed the other way around. So starting from the requirements of the LFD, which often leads to an application gap since LFDs are highly standardized and may also show limitations due to antibody specificity, which are not always aligned with reference analytical methods. So when it comes to statistical analysis and the interpretation, it is important to note that there are no fully harmonized or strictly defined rules on how results must be evaluated. Therefore, we based our approach primarily on the ISO 13528, which actually provides guidance for statistical evaluation in interlaboratory studies. So in addition, we also considered relevant aspects from ISO 17034 and also ISO 17043, the standard norm for proficiency test providers, as well as guidance from AOAC, collaborative study guidance, and the JRC CRM certification strategy. So quite a lot of different documents and quite a lot of information we gathered together. And based on these frameworks, we have developed now a fit-for-purpose evaluation scheme for a value to be considered certified. We require at least 8 independent data sets, preferably from multiple laboratories, the use of at least 2 different analytical methods, and an acceptable level of uncertainty. And if these criteria are not fully met, the value is gradually downgraded to indicative or informative values depending on the number of data sets, methodological diversity, and also the associated uncertainty. And this approach actually allows us to include a broader range of analytes in the evaluation while still maintaining a clear and structured interpretation framework. So based on this evaluation approach, we were able to assign values for all major regulated mycotoxins. In addition, we also included a range of emerging mycotoxins, such as acetyldeoxynivalenol derivatives, but also monyliphamine or fumonisin B3. For the regulated compounds, we observed a very strong agreement across different labs and also different analytical methods. However, for the non-regulated mycotoxins or emerging mycotoxins, the situation is more challenging. In particular, compounds such as eniatines or nivalenol showed significant variability, indicating that further harmonization of methods and standards is still needed. As an example, this slide shows the results for aflatoxin B1. The upper part represents data from ISO 17025 accredited laboratories, mainly national reference laboratories and official control laboratories, while the lower part shows results from non-accredited labs, including universities and industry labs. What we can see here is a very good overlap between the two data sets, based on the information here in the box plot overlap, confirming both the quality of the material and also the robustness of the study design. So for us, the next step is now to bring this material and also future materials towards accreditation and also to further expand our portfolio, what we will do, especially in the feed area, but most likely also in other areas with other matrices which are already in development. And with that, I'm already coming to my summary slide. So we could see that reference materials are a fundamental element in analytical chemistry, and they define the reliability of our results. However, not all reference materials are equal, and factors such as purity, traceability, or proper quality control play a very important role. As we have seen, advanced analytical techniques alone are not sufficient if the underlying reference materials are not of the highest quality. In many laboratories, significant investments are made in highly sophisticated instrumentation, such as triple quadrupole MS or high-resolution mass spectrometers. However, the overall analytical quality can still be compromised if insufficient attention is paid to the quality of the reference materials used. And this actually leads to my final key message. Your results are only as reliable as the reference materials behind them, or in other and more simple words, you can see it here in this picture, a chain is only as strong as its weakest link. And with that, I have reached the end of this webinar. Thank you very much for attending,